Hi, my name is Joshua Olasoji, and today I would like to discuss what's called lithium-ion recycle systems, which is actually the topic of my research internship last summer. Now, to begin, I would like to very quickly highlight what the problem is. With the recent explosion of electric vehicles like Tesla, we have been moving as a society towards more sustainable forms of transportation because theoretically, powering your car with a lithium-ion battery or with multiple lithium-ion motors should emit zero carbon dioxide. However, we're finding that the exact opposite is true. To create all these lithium-ion battery charged cars or powered cars, we have to create a lot of lithium-ion batteries. And the creation of lithium-ion batteries is actually very unsustainable for the planet because mining for lithium ions requires a lot of energy. The current method of mining for lithium ions involves pumping brine from deep within the earth and then going through an entire process where the brine is placed on evaporation pads and then treated with different chemicals and different reactants. And then after 6 months to 2 years of processing, we end up with lithium carbonate, which is the powder that's used to make the lithium ion batteries. Now, this entire process requires a lot of energy. And to produce all that energy to run this process, we end up emitting more CO2 than CO2 is actually being saved by using electric vehicles, which is a bad thing. So during my research internship, I actually went over what's called lithium-ion recycle systems, which basically is a solution to this, where basically we're making the process of mining for lithium ions much more efficient, energy efficient, such that less CO2 is emitted to produce the energy needed to make this process work, thus making the planet a more sustainable place. So how it works is basically there's a chemical reaction called electrically switched ion exchange, or E6, where basically we have two electrodes, they're both platinum electrodes, inside of what's kind of like a fuel cell because everything is smashed together, but it's not like a fuel cell, right? We'll just call it a test cell. There's two platinum electrodes. One platinum electrode will be charged with a negative charge and is coated with what's called lithium manganese oxide, which acts as a lithium ion sieve. In short, basically it attracts lithium ions, right? So there's a manganese oxide on this platinum electrode and it attracts lithium ions. On the other electrode, there's a positive charge going through it and there's already lithium ions on this electrode, right? So when the positive charge runs through this electrode, lithium ions separate from the electrode. So in short, in this electrode, brine will be pumped in, which has all the lithium ions attached to other salts and other compounds. And basically what will end up happening is that when we charge an electric current into this electrode, what will happen is the lithium ions will be uptake or adsorbed from the brine solution and attached onto this electrode. Then we'll move this electrode and over here, and then now that the lithium ions are on it, we'll then pump in an electrolyte solution of lithium chloride. And so then once a positive charge goes in, the lithium ions detach from the electrode and increase the concentration of our electrolyte solution, thus separating lithium ions from brine in a process that is much faster and much more efficient. Now, the analytical methods that were used here is basically the lithium manganese oxide or the lithium sieves that are coated onto each of the platinum electrodes have to have really near perfect crystalline structures such that the manganese oxide does not end up decomposing or degrading during the process. To ensure that the crystal structures are there, it is analytically determined using what's called powder X-ray diffraction, or XRD. Now, the brine and electrolyte solutions that end up pumped into the cell, their concentrations are analytically measured by what's called inductively coupled plasma optical emission spectrometry, which those are the analytical methods used in this test cell. Now, in the end, speeding up the process of mining or extracting lithium ions from brine reduces the amount of energy expenditure and thus reduces the amount of carbon dioxide emissions during the entire process of making lithium ion batteries. And thus, when we use these lithium ion batteries for cars or for other sustainable efforts, right, we end up reaching a future that is more carbon neutral. This ends up connecting to number 13 on the SDG goals for the UN, which is climate action, where basically in this process we are reducing carbon dioxide emissions and thus are making combating climate changes and its impacts. Another goal that it's reaching, or that it's hitting, is goal 7, which is affordable and clean energy, because with the advent of electrically switched ion exchange and lithium ion brine mining, basically we can reduce the energy cost to extract lithium ions from brine, thus making the production of lithium ion batteries cheaper, right? Which means that electric vehicles can also be cheaper, which means that more people cannot use fossil fuels to burn and to power their cars and thus emit less CO2. So we're also making sustainable options, sustainable energy, more affordable. It also applies to a couple other goals on the UN, such as goal 9, which is industry, innovation, and infrastructure, because it's fostering innovation and sustainability, right? But it's mainly number 7, which is affordable and clean energy, and number 13, which is climate action. Now, doing research on this topic, I've actually made a website, which I'll very quickly try to show on my tablets. Here. It's called Lithium. If we scroll through, I kind of talk about the whole Tesla situation and why mining lithium ions is bad. Here I have a couple charts on the top contributors of making lithium ion batteries and who and what countries mine lithium ions. Here I talk about lithium ion mining a little bit more. Talk about the effects of lithium ions. I made a whole company name because this is part of my internship. And here is a little detailed graph of the electrically switched ion exchange, which would take too long to explain right now, but that's basically the reaction that's going on. And yeah, there's a couple more things here. I designed some test cells myself. I 3D printed them. I have a video on YouTube. I talked about the economic and ecological effects of putting this, or of using electrically switched ion exchange and lithium brine mining. And then there's a bunch of sources there as well. And I will be posting all of these sources as well on a doc for this assignment. And yeah, that's basically it. We need to use electrically switched ion exchange. Yes.